Thank you. Thank you for the invitation and the opportunity to present some of the work we are doing at UCL in this area. Is there a pointer, maybe? Okay, so I would like to say straight away that the main person beyond this angle of work in our group is Andreas Hauptmann, we've just lost to ULU, but he's retaining some sort of partial appointment, as seems everybody at UC who once passed by UCL. Okay, so and the other people is former postdoc in our group now at CWI in Amsterdam, Felix Luca, and the other people are from medical physics or computer science at UCL, and Jonas Adler from KTH. Okay, so coming from the more tomographic background, you will have to bear with me through few more slides on the application. So you have seen the photoacoustic application flashing by in a couple of talks in this meeting, but it takes a bit more central, the application takes a bit more central stage in our work, so I need to spend a bit more time on it. So the basic idea behind the photoacoustic is to exploit the difference in the oxygenation in the blood. So this is a clinically relevant parameter, and this happens to occur in a wavelength regime which we can penetrate into the tissue to a certain degree. Okay, so the penetration is not great, so we are talking about a range of centimeter of penetration. Basically what we do, so we put an impulse of the light in this regime, which is near infrared, and into the tissue, and then this propagates through the tissue. So this propagates in some kind of diffusive regime, and according to the optical properties to the tissue, is going to get scattered and absorbed. So in the end of the day, what you get the distribution of the light in the tissue, and this is called fluence. And this fluence is going to be absorbed proportionally to the optical absorption coefficient of the tissue. So this absorbed energy then is getting to be it's virtually transformed into heat, given some kind of proportionality coefficient that we don't care so much about, and this gives rise to an acoustic wave. So this heating up increases the pressure in the tissue, and this pressure is released in a form of the acoustic wave. So this is kind of the cartoon, and this acoustic wave propagates then to the surface of the sample. And in our case, we look at the geometry where we measure the acoustic pressure time series. So we measure this wave pressure over time at the surface of the sample. Okay, so this can be mathematically written as a wave equation, and bearing with some kind of functional setup, which we like to work with this smooth with this C infinity functions, because most of the solvers for the wave equation that we use live or thrive in this type of functional setting, but not being too obsessed about this. So basically, we have an operator that maps the initial pressure that is compactly supported in some kind of domain which is much smaller than RD. And then what do? We measure it at the surface of the sample in over some kind of finite time. So this wave should pass in 3D, so that's not a big issue. But from the point of view of the setting up, functional setting up, we need to input this smooth window, so for our math to work basically. So given this kind of setup, we have the initial problem for the wave equation, and so the C denotes speed of sound that could be spatially varying, and then we have the initial conditions. So there is this condition, this first order derivative corresponds to the fact that the process is happening virtually instantaneously, and this is our initial pressure. Okay, so we have this initial value problem for the wave equation, and to give you an idea how does it look like. So this would look somehow like that. So if you have initial pressure that looks like my university logo, then this is how the propagation of this looks like, and basically the data is being recorded at the sensors around, and so this is my photoacoustic data. Okay, so I will also need the edge join operator. So the edge join operator goes backwards from the data to some sort of back projection of the data. And this happens to correspond to a different wave equation. So it is again an initial value problem for the wave equation. This time the initial values are homogeneous 0, and then we have a source term. So this is the time varying source, in which source term the data measured at the surface of the sample are plugged backwards into the backwards into the domain. Okay, so we have the time varying source that corresponds to the reversion of your data. Okay, so this is the edge join operator, and then doing the same thing again. So this is if I had the adjointed the UCL. This is how it's going to look like. Okay, and then of course this is conveniently in the way on the most. So it looks to you like an inverse, but it's not quite. So there is something happening here. It is also oversaturated. So I had to clip it. So basically it's slightly different than the inverse, and which is the so-called time reversal operator. So this corresponds to the inverse operator. I put approximate here for a reason that this only kind of is an inverse operator under very, very clinical conditions. And this inverse operator corresponds to the, again, initial value for the wave equation with the homogeneous initial conditions. But now we have something that is like a constraint at time-dependent constraint on the sensor. So basically the data is again being played back, but in the form of the time-dependent constraint. So if you have this planar sensor geometry that I am using, you can think about this as a boundary value problem, but it's just because of the way how this geometry deals with the symmetry of the solutions, we can get the complete Cauchy data here. Okay. So the inversion of the UCL looks then like that. Okay, so this is now, though you cannot quite see it, so this doesn't have artifacts now, and so it is basically good. So there's some smoothing going on in this whole business, but this has to do with the reason why we had to assume the C infinity for the functional setup of our problem. Okay, so these are the operators that will be involved: the forward adjoint and the inverse operator, and the data that we obtain are kind of very high resolution. So this is the second part of the problem here, and this is due to the fact that we use this planar sensor, so this is virtually an interferometer. So it is the same technology that was used basically to detect the gravitational waves, but there is pushed to higher level of sophistication. But basically you have two mirrors. When the acoustic wave impinges on the mirrors, it changes the separation, and this change in the separation can be optically read out using a laser, and this is how we obtain. This relates to the pressure of the wave. So using this type of technology, we can just sample the pressure on the detector very, very finely. So basically how it happens is you excite, so you put the impulse of the near infrared, so to excite the optical absorption and then acoustic release, and then you record at one point, you record the whole time series, okay? And then you can move the focus of your laser to a different point, and you can sample this detector as fine as you wish. Of course, it is inherently sequential process, so it takes time, okay? So then you can obtain images looking as fantastic as that, and then because we are in 3D, so the images that you're looking at are so-called maximal intensity projections. So this is looking from the top, and it is looking from the sides, and the maximal, it's just looking at the maximal intensity along the lines. Okay, so basically, so we have two things here. So we have a lot of data that we take time to acquire in practice. So we have spent some time optimizing the hardware, but still we will, in many applications, we like to subsample or use compressed sensing if there's another line of work. And the other thing is that as far as the linear operators goes, or linear inverse problems goes, this one is expensive, okay? So the people who work on nonlinear inverse problems, of course, can claim that they are even more expensive, but this is a linear problem, and this is more expensive than the other ones. Other ones, for example, the canonical ones being the CT and the MRI. Okay, so now I'm going to switch more to try to abstract for a moment from from the physics here. So the setup is, so we are going to have a true solution in some space of X, and then we are going to have the data that is in a space of Y. We have a forward operator that maps from X to Y, and then we have the measurement that is, of course, corresponds to the forward problem plus some kind of noise. And then for our path operator, this is going to be A is equal to P, and then Y is equal to G, where G was my data. It's now sampled at times at the detector points. And yeah, so just to connect the two things. Okay, so you have heard about this idea a few times. So what we want to do now is we want to construct some kind of map that goes from the data to the solution. So in a kind of conventional way, this would be could be a pseudo-inverse, for example. But for now, so this is some map that takes the data into something that is hopefully close to the true solution, and so this map can be parametrized by some kind of, you can come up with a clever formulation of that. You can parameterize it by some sort of parameters, and now of course you can learn this parameter. So this is something, for example, that Ozan and Christoph have been doing before. And so basically people came up with two ways of doing it. So the first one is the less expensive one. So you kind of invert your data in some kind of canonical, with some kind of canonically simple way, very approximate. So for example, an example of this would be taking a back projection without the filter, though I don't know why one would do that, but the other option would be, just to apply the, for example, filtered back projection to the limited data straight away. And so this, of course, is going to come with the reconstruction coming out of this is not of high quality at all. So you have to do something to it. And then the idea was to post-process it with some kind of CNN, for example. Okay, and then there is a number of works that have done that. And an alternative idea is to basically take a couple more steps of the same. So it's the idea is to unroll an operator basically and into a couple of iterations, and then at each iteration to learn an update that takes some information available in this iteration. So if you go with the standard gradient iteration, so you're going to have a gradient and a former iterate, and then you are going to feed it into your, as a parameters to to your operator that you have learned, and then you are going to update like that. So there was a number of works along these lines, and then of course there's the same what Ozan was talking about. Okay, so the idea here is that this k is going to be, so this xk is going to be good, so close to x2 much faster than in the conventional, if you have run the conventional methods, just that uses this inputs here, so something like a gradient descent, for example. So why is it interesting? The main point about this is that this guy is expensive, so you want to limit the number of application of this. Okay, so what we've been doing in the photoacoustic, we've been mostly looking at the second approach. I mean, we compared to the first, of course, but yeah, okay. So the second is, of course, more sophisticated. So the conventional way of inverting in photoacoustic will be to solve some kind of optimization problem, which balances the data fidelity in some kind of a priori regularizer. And if you take the forward-backward scheme, so as I was saying before, so it would be kind of you would have the gradient, and you would have the proximal operator corresponding to R. And have this kind of simple scheme that is completely deterministic, that uses the gradient information in a previous iterate, and of course assumes the knowledge of R. Okay, so especially in the photoacoustic application where you have these vessels, so we've been trying to look at these vessels with many different analytic formulations, and of course not as sophisticated that I have seen in this meeting, but just looking at this in terms of total variation or curvelet functions and so on, did not yield very successful regularization. Okay, so these things don't tend to be very sparse in those deliberately constructed regularizers. So the idea is now to okay, so if you cannot characterize it, so let's have an implicit characterization. So you will give a bag of vessel images to the net. It's going to learn how kind of vessel images look like, and then hopefully we are going to come up with some kind of implicit representation of this operation, okay? And now there is nothing more claimed about this. So there's nothing claimed, no proximal operator properties are claimed or anything, so there is no theory. It's just praxis. And yeah, so okay, so I guess the other two choices that you could have for R would be, for example, have a non-negative least squares. So this is this corresponds to the indicator function of the non-negative real, and this is of course the proximal operator for that, or the a priori mentioned total variation. Sorry, so total variation function, which you know you need to solve iteratively for the proximal operator. Okay, so to convince ourselves that you know how far we can get with the iterative regularization using this type of non-negative least squares and total variation. So we kind of look at this very simplistic phantom, which is going, however, to exhibit the typical artifacts that come from the limited view in photoacoustic tomography. So we have a kind of rods here, and then we look at this at the top of this pink area is the sensor. And so this is the cross-sectional view. Of course, there's no more action than that in this. And then there is a kind of 16-fold random subsampling pattern. So if you would measure everywhere and then you would just adjoin the data, so this is slightly different to the time reversal, but it's not hugely different, and the artifacts are kind of similar. And so this is what you get. And if you do this to the subsample data, so this is these artifacts get different, let's say. And then after 20 iterations of the non-negativity constrained least squares, this is what we get from the full data, and then if you have subsample data, so this is what you get. So there is still kind of some kind of noise in the background. And now TED-TV can dispatch it pretty well. Okay, so TED-TV on the subsample data performs quite well here. So this is basically how far you get, and then the point is you can get there, but you need to iterate for a while if you have a good regularizer. Okay, so I guess I've said it before. So the in our application, the forward operator is quite expensive. So it is expensive because the cost, if you have even in a volume n by n by n, so your cost will be n squared times log n. As a usual cost for MR would be, for example, n cubed for log n. So we are kind of having to deal with 1 over order n here in this solver. So we are even more interested in exploiting the fact that we apply as few of those operators. So this is the same cost for all these wave equations. So there is no difference between time reversal, adjoint, and forward. Okay, so we kind of encountered so this 1 order n definitely made it infeasible to unroll the few iterations of this iterative procedure and learn 5 networks at the same time. Okay, so what we had to do, we had to kind of take the greedy approach. So we are going to train 1 network. We are going to compute the gradients. We are going to train the next network and compute the gradients. So I'm not sure if this is coming better when you write it down in a equation form. Upsala. In the form of equation, but this is basically, this is the idealized situation when you can train for all your intermediate networks. You can minimize this error, and in our case we minimize for each of these parameters separately. Then you can compute then we get the next iterate here to plug into our next optimization stage. So you get a monotonic scheme. Yeah, of course not optimal because we are restricting the space of your solutions, but it seems to work quite well. And so, yeah. So what is good about this approach is that you don't have to say a priori how many levels you have. So as long as you keep descending, you can keep optimizing, and then you can stop. And also, you can use after each stage you have a meaningful output, because in each stage you are trying to minimize something. And yeah. Okay, I have said it before. So this is the type of data we want to reconstruct, and to train this we had to just get some vessel images. So the vessel images had been taken from the CT database and from the lungs. So basically, Andreas has segmented 1,200 volumes out of the CT lung images of this size. This size is just the size of the photoacoustic data we collect. So this is how the kind of isosurface plots of these guys look like. And he used this as a training data. Okay, this network, so this stage by stage, in this stage by stage approach, each network took for 50 epochs took 1 day to compute, and on top of that comes computing of the gradient, which is the forward and an adjoint solution for your data set. So altogether 5 days for each training, each network, and 2 days for computing of the gradients gives you 7 days. So the projection of how many days it would take if you would like to have this approach that is optimal of training the 5 things at the same time would be about 70. So I didn't have enough faith, I think, in the thing to wait for 70 days while it is crunching. So these are the results. So there's kind of a phantom So of course this is all synthetic data. So we pick one out of them. So this is not in the training set, and then we are initializing it with the back projection, and the result that we get from this reconstruction after 5 iterations is this. So it's pretty good, and we were happy with that. And then we compared it, of course, to the application of the UNet, which is the post-processing. So the network that is employed here is very simple, okay? So I do not have time to talk about this, but it's nothing special, just really small filter, convolution with small filters, and it doesn't have this UR architecture, and but it has a skip connection. Why this is the full-blown UNet used for the post-processing, and the difference is, and this is basically the difference. So the difference image between the ground truth and then and the UNet, and the difference between these 5 iterations. So you can argue that it pays off to go to do this iterative scheme. So the same is belabored here on the error plot, so taking over some samples that were not in the training set. So you can see that the UNet, so this is our initialization point, and this is where the UNet gets. Of course, UNet is inherently one iteration, so that's why it sits here. And then the conventional non-negative least squares, and then the total variation conversions you have here, and of course they take a long time, and they would go further down, most probably given opportunity, while you get the learned method kind of after 5 iterations coming here. So we kind of feel quite justified that there's no point to try to push it any further in terms of iteration. So it kind of got where it's going to be. Yeah. Okay, so now if you take this, of course, they are not going to be happy with reconstructing the synthetic data. So applying this learned network naively to the real data results in this. So there is a lot of features in the real data that was not present in the synthetic data, and then you can do a lot of tricks. And the best trick to do is to perform a transfer training, and then so basically doing transfer training on the real data. So first of all, we're heavily restricted in the number of the data sets that we can train on. So we took about 20 fully sampled measurements. So with this fully sampled data, we could perform good quality total variation reconstruction on fully sampled data. And then there's, of course, bias of this whole procedure is now towards total variation solution. And if you have done that, so there is no gold standard, other you start to cut out the tissue and look at this somehow like that. So this is the result after the retraining, and this is the result corresponding results from the 20 iterations of total variation. So and then there's fourfold gain in time to apply the learned method. And so this is the fully sampled reference reconstruction. Okay, so so this 7 days, of course, is expensive for training, and it also still takes 2.5 minutes to apply. So in a sense, if you acquire this data and sit in front of it, so it's not nowhere close to real time. So if this is your goal, so we kind of ask the question: so what happens if we instead of having this highly sophisticated wave solver, we will work with the Fourier inversion. So the Fourier inversion, first of all, only will work for homogeneous speed of sound, but you can argue that unless you have a scanner that couples both measurements, you don't know the speed of sound. So you are not using this in the reconstruction, so that's fine. But the other thing about the Fourier inversion is that it is, as you will see in a moment, the inversion procedure is fine, but you need a forward model for the iterative scheme, okay? And so this is an issue. Why is it an issue? So, so this is if you transform the wave equation in a Fourier domain, so you get this dispersion relation, and then this dispersion relation gives you the following. So you can map the data and the initial pressure in a Fourier domain using this map. Okay, so this is the equivalent. There's a equation we get. So there's a factor here, and of course there's a singularity here, is along these lines here, and so there is this remapping going on. So basically, what you have here, so this colorful region corresponds to the range of the photoacoustic operator, and in this range, this contours that you have, so this is basically a hyperbolic transformation. So this corresponds to the constant frequencies in an image in the z direction. Okay, so I have a sense of that this is 2D visualization, something that would generalize to 3D, but just 2D is easier to look at. So this is my sensor. So this is my time. So this is my data domain. So this is in a Fourier space. So this is the range, and then for the I have the mapping that this data corresponds to this to this Ks and constant Kz. So this is the mapping that I get. And what makes us the headache, of course, here is this factor here. So this factor will blow up close to this asymptotics here, and we have to do something about this for the forward problem. So let me very quickly show to you how the inverse formula that is used in practice heavily looks like. So that of course has the factor the other way around. So you are not worried about the singularity here. And so basically, you get the solution, by inverting the 3D Fourier transform. So this is the same formula, and just inverting the standard three-dimensional Fourier transform. And then the factor that I get here is, of course, quite benign. It is 1 here, and it decays towards the 0, towards this asymptotics here. So that's fine. And if you try to use it for the forward problem, of course, the X factor is 1 over. So what happens is that it is nice here, but then it starts to blow up here. So I had to take a log to get some sort of visualization here. And so basically what you have to do, you have to somehow take care of it. And one way of taking care of it is to perform a cutoff along the contour line. So if I pick a contour corresponding to, so I can conveniently picking a contour that gives me a nice expression on the on this side. So if I pick a very particular form of this contour, which corresponds just to some contour in this plot, then I can get my I can get an idea what data I'm going to restrict to. Okay, so instead of having the whole range, I'm going to restrict my data to this kind of smaller bow tie. And physically, this means if you take this parametrization, this means that we have the sensor here and the wavefronts coming on the difference. So this is a wavefront vector. So I'm going to restrict my wavefront vectors. I'm not going to allow them to go beyond certain angle. Okay, so it's like this. There is a certain cutoff angle at which I'm not going to record the wave anymore. It is quite a physical assumption actually, because the sensing element is not completely angularly uniform. So you could of course think about other ways of doing it. So going along the contours, for example, of this filter, and so going along the contours of the filter is not going to be good in its own right, but merging the two is actually quite a good idea as well. So merging this cutoff with going along the contour up to here, then going to the cutoff and going to the contour here. Okay, so basically we are regularizing the forward operator now, and this is the effect. So this is the phantom, this is the ideal data. So ideal data here is already limited angle data, of course, because otherwise it would have to be, the plane would have to be infinite for the finite data. But so putting in an angle of 45 kind of causes this type of artifact in a reconstruction of the, so this is how the Fourier space of the data looks like. So this is how the inversion of from the Fourier space of the data looks like, and this is when you allow a larger angle. So this is how it looks like, and this is how it reconstructs. Okay, so yeah, so you have so some of this is a limited data artifact. So this is micro-locally justified to happen, and then some of those stuff is of course coming from the cutoff in the Fourier space. We're missing some frequencies. So, so from now I'm going to now denote this forward operation by AF, and then the backward operation by F dagger, and then I would like to caveat here that actually now it is not a gradient. Okay, 5 minutes? Oh, yeah, sorry. Okay, this is actually not a gradient anymore here. Okay, but it is the time reversal based method that kind of you can do exactly the same with the time reversal that you do with the forward backward. So you can imagine that instead of your gradient you back project your residual. So if you do that and call it gradient, that is exactly the same method, and it corresponds to the taking the projection of the back projected residue. Taking the gradient of the back projection residual. Okay, so you can do the same with the time reversal. The ideas are based on Neumann series rather than on the gradient descent. Then, okay, so and then brutally not going to make a difference between the two. Okay, so but the results are actually generated with the time reversal version. Okay. So now we take this unit, the smallest unit, I guess, I mean the 2-point unit in terms of points per letter. So we put a little bit more into the network because we expect some aliasing basically from the missing frequencies in the Fourier space. Okay, so to be able to take care of it, we want to have a little bit more of this imaging friendly structure in the net. And okay, then the threshold angle that we used was 75 degrees, and yeah. And this is what you get this is what we get for the human in vivo. So this is the fully sampled reference frame. So this is the 20 iterations of the total variation. That takes 10 minutes and gives you this PSNR. And this is the 5 iterations of FFT path, which is the path with the FFT forward and inverse, as I explained. So this takes 20 seconds. Okay, so this is now getting in the area that is interesting, because this is something that you can, while you collect stuff in the lab, you can actually react to what you are doing. Okay, so all the usual caveats apply. So for the best results, you need to retrain. So basically, so this results were already generated in kind of a little bit more flexible framework. So I think there was a variance. There was a variance in various parameters allowed. So variance in the speed of, a little bit of a variance in the speed of sound in the training set, because it was for the synthetic data. There was some difference allowed in the sampling pattern. So the sampling pattern resembled our multi-beam scanner pattern, and possibly something more. So there was already some kind of flexibility input into the training. It was trained on the synthetic data and then trained up on a set of photoacoustic data, and then still we try to apply it to different data. And so this is basically what happens there. And I think this is kind of quite canonical across all of those examples. That so if you spend 10 minutes with the TV, so this is you are going to get TV close to whatever your sample on the right-hand side is, where you kind of have some kind of problem with the contrast with the net learned approach. So there is some kind of loss of contrast for this. And then if I scroll through, so all these images are exactly the same arranged, so you can see similar situations. So there is some kind of loss of contrast happening here. So this is not so much here. So apparently this was still happening. So this is now here's the contrast is enhanced. So there is some kind of issue with that. So this is maybe quite all right. So this was maybe similar to enough to what was trained on. Okay. And then there's of course over-exaggeration that actually happens already in the TV. So that could be the bias, partially the bias that we input into our training by virtue that we don't have a ground truth and have to train with something. All right. Okay. Thank you very much.
Questions? Thank you for the talk. If I understand you correctly, you train your network to perform one iteration, but from a very specific starting point and then along a very specific path,
yes.
So to say. Now, would it work if you trained the network to do just one iteration, but for a range of starting guesses, and then would just apply the same network many times to the starting point that you get from a previous iteration, and then go with the same network?
I don't think so, because there is the kind of the power of this approach is on that it has been through the A transpose a couple of times. So this is of course enhancing the modes that are present in the operator. So I don't think that is the same. I don't think that is that what you could get.
Well, you would still use the forward operator. You would do the same thing that you are doing, but
yeah,
just,
but
just train once and then apply.
You would take away the power. The power, if you apply A transpose to something that was A transpose to something that already had AA transpose previously applied to it. So this is usually how you emphasize in your initial started vector the information that is contained in your operator. So I don't think that would work as well.
Okay, thanks.
Yeah. Another question? No? Okay, so let's thank the speaker again.